Hi, and welcome to part 3 of our Flow360 training. Looking at our expanded visualization of the training structure, you can see this session will provide an overview of the Python API. For today's introduction training, we'll cover 7 topics. It will start with the Python install process, then a brief overview of the documentation and GitHub page, then details on the unit system and entity creation, basic cloud operations, how to put this all together, and then we will conclude with a demonstration of the full workflow. Now let's jump in. Installation is very straightforward, as it can be done using a pip install. This will install the latest solver version on your machine. After that, you will have to configure your API key. This can be found by logging into the web interface of Flow360 and going to your account information in the top right corner. From there, you will open Python authentication and show your API key. You can copy this API key and then run the command provided in the online documentation with your API key to authenticate. To ensure everything works correctly and there are no issues, we recommend you run the simple script provided in the Quick Start section of the documentation. If you have any issues, please reach out to us and we will work with you to address them immediately. Now we will cover our Python documentation, which is available through the same online documentation shared in the 2 previous training sessions. Go to the documentation and select Python API. This provides instructions and scripts on how to install and set up the Python API, how to configure your API key, and testing if the installation is working correctly. This is also where the API reference is located, which provides all classes, methods, and parameters needed to perform your Flow360 simulations. Let's move on to setting up Python within your interface and using Flow360. We recommend using an IDE like VS Code, PyCharm, or something similar. The reason being is this will provide autocomplete suggestions, the structure of an object within the code, and the attributes, as well as an example. Many of the concepts discussed in the web interface training carry over to the Python API as well, making it easy to transition between them. Moving to discuss entities. There are multiple methods you can use for assigning to entities and utilize downstream when setting up the mesh or the case. You can either use groups assigned during geometry creation, or use the asterisk feature to select multiple components that have not been pre-grouped. An example of this can be seen on the right side of this slide. The code snippet at the top is a command to show the available grouping within the geometry and will print out the existing grouping. It is grouping edges and faces by tag. Then, when you generate the mesh, you can apply a refinement based on that specific grouping of edges. If you are creating new entities using Python, we support cylinder and box volumetric entities. These would be used for something like mesh refinement or assigning volume models, such as BET or porous media. Output entities can also be created using points or slices to help with post-processing. Moving on to units within Python. Unit systems are always defined at the top of the script. You can see in the example on the top right that we define the SI unit system. All script after this will default to the unit system specified. Instead of SI, you can also use CGS, or the imperial unit system, or overwrite and specify the new unit measurement, like in the example shown in the bottom right script. The only time you must specify a unit is for angles by defining either degrees or radians. Dimensional quantities can be used throughout, but string inputs must be non-dimensional. Examples would be if you are using a particular initial condition or using a user-defined expression. To re-emphasize how units can be used, the 2 scripts on the right do the same. You can see the top one specifies the unit at each line, while the bottom one provides the unit system at the top, and units are inferred after. Unit documentation is available at the link provided. Next, we will discuss how to create a new project with Flow360. Similarly to the web interface, projects can be started from geometry, surface mesh, or volume meshing using the Python API. While creating a project, you also need to define the unit in which the geometry or the mesh is being imported and the name of your project. If you want to use existing objects from a project created in the web interface, you can reference the ID of the object. That can be all IDs listed in the last training, including project, geometry, mesh, and others. For submitting cases to solve, you must create a project before submitting. You can see an example of this on the top right, where we set our parameters and then give a name to the case. This takes all the settings from the parameters and launches the case. If you want to fork a case, you can apply the same logic, but add an extra attribute, which is fork from, and this will initialize the solution from the previous case. Now let's discuss the params object shown here in more detail. Params is a data structure that contains all mesh and solver settings from your case. You can think of this as taking all of the information from the simulation setup panel in the web interface and structuring it into the same objects class in Python. To help explain this further, let's do a quick demonstration. What we are going to do is create a new project from geometry and then set up the mesh, case, output, and then launch the case. If at any point you need support on how to reference something, please go to the Flow360 Documentation API reference section. Let's start at the top of the script. First, we will import Flow360. This gives us access to Flow360's project creation, meshing, solver, and output controls directly from Python. Next, we create a new project directly from a geometry file. This line uploads the geometry, creates a new project in your Flow360 workspace, assigns the project name, and defines meters as the base unit system. Alternatively, if you already have a project in the cloud, you can reconnect to it instead of uploading a geometry again. That's what this commented line is for. Now we create a reference to the geometry inside the project. This gives us access to the geometry so we can group faces, select surfaces, apply boundary conditions, and define outputs later in the workflow. Next, we define the output fields we want to export. These lists simply define what data Flow360 will compute and write out after the simulation. Keeping these at the top of the script makes it easy to reuse or standardize outputs across multiple cases. Now we group geometry faces using metadata from the CAD file. This organizes surfaces based on a face ID tag, which makes it easier to target specific regions later for boundary conditions, refinements, or output extraction. You'll see these groupings reflected in the web UI geometry tree as well. Next, we enter an SI unit context. This ensures that all dimensional values inside this block are interpreted consistently in SI units. It's a simple way to avoid unit mistakes when specifying operating condition, surface, and volume mesh settings. However, you can still overwrite settings with another unit if you want. Now, for creating the far field region, we'll use Flow360's automated far field option, which determines and creates the appropriate far field dimensions based on the geometry. If you have your own far field geometry, then you can use the user-defined option. No changes are needed for this model, since the far field is automatically created at 100 times the model's maximum dimension. Now we define the main simulation parameters. This is the Python equivalent of the setup panels in the web UI. Everything related to meshing, physics, solver settings, and outputs lives inside this structure. Starting with meshing, Flow360 uses an automated meshing process that reduces the amount of input required for the user by providing default values that are sufficient to generate a high-quality mesh for most cases. As you can see here, we only have to provide a surface max edge length and first layer boundary layer thickness. Advanced parameters are available, but not needed for this model as the default values will create a high-quality mesh. Next, we will define a refinement region around the aircraft, which helps resolve flow features in the near field and wake. We will specifying the refinement region to be a box, then provide the name, axis, and angle of rotation, center, and size. The Python script can also be launched in draft-only mode, which will help you visualize the refinement box in the web UI as well to verify its placement. Next, we will specify reference geometry values, which will be used for non-dimensionalizing lift, drag, and other forces and moments to get the force and moment coefficients. Next, we define the operating conditions. This sets the free stream speed and angle of attack for the simulation. One advantage of the Python API is that sweeping over angle of attack or speed becomes straightforward to automate. We then configure steady time stepping. This sets a steady-state solution with adaptive CFL control. For unsteady problems, this is where you would switch to a time-accurate formulation. Now we define the physics models. First, we apply wall boundary conditions to all geometry surfaces. Then we apply a free stream condition to the far field. Next, we configure the flow solver and turbulence model. Here we explicitly set solver settings related to Navier-Stokes, turbulence and transition model, and their advanced parameters. You can rely on defaults or fine-tune these settings for more challenging flow regimes. Now we define outputs. This tells Flow360 what data to save and in what format. In this case, we export both volume and surface data in TechPlot format. Additional outputs like slices, monitors, or streamlines can be added here as well. Finally, we launch the full workflow, which sends the simulation to Flexcompute's own GPU cluster, powered by the latest high-performance GPUs. The job is instantly picked up and assigned to the optimal quantity of GPUs based on the size of the mesh. While the case is running, you can open the web UI and watch everything progress in real time. The project tree updates as each stage completes, just as if you had launched the run directly from the browser. So whether you use Python or the web UI, you're working with the same solver, the same infrastructure, and the same project environment. The Python API simply gives you a more scalable and reproducible way to drive the workflow. This concludes the demo portion on how to create a project from a geometry. Now, I would like to show a custom feature we created to automate report generation for your project. This script is available in the Flow360 examples repo on GitHub. It will pull all the information from your project and export out everything into a PDF report. The script defines different locations. You want to add slices and different camera angles to capture a post-processing image. The output of the report looks like this. It provides a summary of the cases run, the inputs and statistical data for each. All material from the Analysis tab, including the charts and visualization, can be embedded. This script can be customized to your needs to automate your post-processing workflow, all within Flow360. Now we can go through one more brief demonstration on how to run an alpha sweep and how to use warm starts so each new simulation is initialized from the previous one. We want to evaluate aerodynamic performance across multiple angles of attack. In this example, we will run angles from 0 to 20 degrees in 4-degree increments. Before launching the simulations, we create storage for all case names and case IDs so we can automatically save them for post-processing. An empty list is created, and every time we launch a case, we append the case name and ID to that list. We start with the template case setup. The base parameters are already defined. The script loops through each target angle of attack, updates the alpha value in the parameter object, and then launches the job. Next, we define how long each simulation should run. Lower angles of attack are easier to converge, so they use the default 3000 pseudo steps. Higher angles of attack are more likely to approach separation and typically need more iterations. For angles above 10 degrees, we increase the run length to 5,000 pseudo steps. Now we decide how to initialize each simulation. For the first angle, alpha equals 0, we perform a cold start, meaning the flow field is initialized from scratch. For every angle after that, we warm start the simulation using the converged solution from the previous case. For example, when we run the 4-degree case, we initialize it using the solution from the 0-degree case. This makes convergence faster and improves stability. In practice, the script forks each new case from the previous parent case. 0 degrees runs as the base case, and every higher alpha case is launched as a warm start based on the 0-degree solution. As the script runs, it automatically saves both case names and case IDs. After the sweep is complete, that list is exported to a CSV file containing each alpha case name and its case ID. This CSV can then be used during post-processing to download results and build aerodynamic databases. This workflow is a practical and efficient way to run an alpha sweep and is commonly used when generating aerodynamic databases with Flow360. With that, we have now concluded the third training session on the Python API. As you continue your onboarding, we recommend that you use and reference the Quick Start Guide available in our documentation. We would also appreciate to hear your thoughts and feedback so we can continue to make improvements and shape the development of Flow360.